Welcome back to ECE 441A, 541A. Looking for the people in the center. Everybody's sitting on the edge, but we'll all maybe get a little bit more warmth in here as more people come in, hopefully. But today what I want to do is go back. We were in Chapter 9 with root locus. We're going to jump back into Chapter 8, but that should be a review for you on Bode Plots, and we're going to then start designing controllers from a Bode Plot sketch in, let's say, complementary to the root locus. So once we sketch the Bode plot, can we figure out how we want to shape those magnitude and phase curves to improve the behavior of our system? That's the idea. Homework 8 is not yet available on D2L. I need to create that and post that, but hopefully it will become available. And I believe December 5th is not that far away. That's only a week after Black Friday. So a week from this Friday is December 5th. Lab number 3 and project, if you're in 541A, are due that Sunday. And our final exam is on the Wednesday of finals week, just as a reminder. And you won't have to come any earlier. It's at 8 o'clock, but you will get 2 hours to complete that exam. That's a 2-hour final on Wednesday, the 17th of December, just to keep us all in the know. And as I said, we'll be talking about Bode plots today, and in particular chapters 8 and 10. 8 being how do you build these Bode plots, and I'm hoping that's a review. And 10 is the design piece. And today we'll talk about the characteristics of a Bode plot, and we'll get into stability margins. Have you seen stability margins with Bode plots before? Show of hands. A few of you, maybe not. If you, well, depending on where you took your previous classes, maybe not so, but it's not a difficult concept. It's fairly easy, and what we will be doing is trying to shape those magnitude and phase curves to improve or enhance our stability margins. And maybe not today, but I think Wednesday we will do system identification based on a Bode plot. Somebody now gives you a Bode plot or the frequency response of a system. Can you extract the transfer function? And that's something that you actually might get experimentally. Somebody might give you, they might say, oh, my network analyzer generated this. And you go, oh, I need a transfer function. Or you could, based on what we learn next, is shape those without needing a transfer function, but it might be helpful to extract a transfer function from those frequency response diagrams or from the Bode plots. Here is basically the table of contents for what we will be doing. The analysis, again, how do you sketch these Bode plots, is in Chapter 8. There's several representative transfer functions in Table 8.5 that you could look at to remind you of what these look like. I believe Table 8.3 shows you or illustrates the basic components, what a gain might look like in terms of a Bode plot, what a single zero factor might look like, what a pole factor or what a two-pole factor might look like. That's in Table 8.3, or the individual factors. Table 8.5 puts all of those pieces together. And the nice thing about Bode plots is because you're dealing with magnitudes in dB, all of these pieces essentially just add together. So if you have a piece, and that depends on you having it in the form of the time constant form, and I hope all of this starts becoming more of a review in nature than new material. But we'll see, and if it is new, it gives you something to chew on in addition to your food on Thursday. You can start reviewing some of this material in Chapter 8. And then we'll look at the design process. That's included in Chapter 10, and these numbers in parentheses after the chapters are the particular sections that you'll find or that we'll be focusing on for this class. So I started counting Chapter 8. That was pretty easy. 1, 2, 3, 4. Chapter 10, I started jumping around a little bit, but that's because we've already covered some of Chapter 10 with the root locus design. So we'll be filling out more of Chapter 10 by dealing with these frequency response depictions or Bode plots. Here are a couple of sentences relative to a Bode plot. The Bode plot provides information about a system's frequency response. And a frequency response, just think of a graphic equalizer on your stereo if you have such a stereo. It's how does your system respond to given sinusoidal inputs? How does it adjust the magnitude? That's going to come from the magnitude plot. How does it adjust the phase? If you now inject a particular sinusoidal signal at the input to this system and you have the magnitude and phase plot or the Bode plots, you can now, knowing your sinusoidal steady state behavior from an earlier class, let's say 320A, you can now immediately write down your sinusoidal steady state output y of t. And that's the concept of the Bode plot. It's really just this, oh, I maybe sketched them too big, but here is a hypothetical magnitude plot, and it's typically plotted in dB versus frequency omega. And in this particular sketch, can you tell me anything about the system just by looking at the magnitude response? And now, after today's lecture, you should be able to say, yes, of course. Now, I don't have anything labeled on the frequency axis, but those bends or breaks in the magnitude tell us something. They tell us there's some factor, either a pole factor or a zero factor, occurring when we see those breaks. And now just think of numerators and denominators, upstairs and downstairs. If it's in the denominator, it's downstairs, your breaks are going to cause you to go down in your magnitude response. Consequently, you should anticipate, the way I've sketched this, is we have two poles in this system, in this particular corresponding to this frequency response magnitude, Bode plot. One of the poles is right here in frequency, and the other one is right there. And the rate of, or the slope, if that's a single pole, is now minus 20 dB per decade. And since the slope changes after that, then we simply keep incrementing by 20 dB per decade. If we had a zero, then that would add a positive, or it would start breaking up if we had a zero factor. The phase curve is a little bit more interesting in that, well, the magnitude curve is easy because you can set it and forget it. I don't know where that comes from, but maybe it's an infomercial. But the magnitude, once it kicks in, once you reach that frequency, it's contributing that slope for the duration of the frequency axis, from that point all the way to infinity. The phase curve is a little more interesting because its change is centered about the break frequency, and it goes a decade before and a decade after. That's the only interval of phase change associated with a linear factor, be that a pole factor or a zero factor. The pole factor will go down, and it will contribute minus 90 degrees over that 2-decade interval. A zero factor contributes plus 90 degrees over that 2-decade interval. That 2 decades centered over the break frequency. Typically, I get lazy and I just say G for the forward block, but that might actually be the combination of a controller, let's say G sub C, and a plant G bar. I've just multiplied all of those together. I now have this transfer function G, and I need to sketch its Bode plot. If I have that G in this standard block diagram configuration, what's the closed loop transfer function expression in terms of G of S? And this one should just roll off your tongue, right? What is the transfer function T of S between the reference input R and the output Y if we have G in the forward path, H equal to 1, we have unity negative output feedback. That's our closed loop transfer function. And we can actually, what we're doing with the Bode plot is we are inferring closed loop system behavior on T of S based on what G of S is doing. That's the idea. We want to be able to infer closed loop system behavior simply by knowing that open loop transfer function G of S. And that's where we will pick up. We are going to say that information from the Bode plot of G of S can be helpful in understanding the closed loop system properties. Meaning if we know what G of S is doing, or if we shape G of S, that's going to actually inform what's happening in the closed loop. And so we'll know how to adjust G of S to provide or produce the behavior that we want in the closed loop transfer function. One of those properties is as follows. Suppose we notice that the magnitude of G of j omega is large at small frequencies. Suppose we look at the Bode plot and we go, wow, G is big at small frequencies. What can we say about the closed loop transfer function T of S? If G is really big in magnitude, bless you, then what's T going to do in that frequency interval? It's going to be less than 1, but if G is really big relative to 1, then it's going to be about 1, isn't it? G and 1 plus G are about the same. So the closed loop is going to be roughly a gain of 1 if G is really big. And what does that mean? Remember what T is. That's just this ratio of output over input. If we inject a sinusoid in those frequency intervals, or in that frequency interval, the output is going to basically be a replica of the input since T is 1. So we'll be able to track frequencies nicely at low frequencies if G of S is big at small frequencies. That's the implication of G being large at small frequencies. The closed loop transfer function has a gain near 1 at those frequencies, or at frequencies where the magnitude of G of j omega is large. Or another way of saying that is, therefore, there is a small error, and I was explaining what we do in this class to somebody, and I needed to enunciate better. More than just two. I said we are worrying about steady state error, and they go, oh, the error, A-I-R, and I go, no, 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 E-R-R-O, error. So the steady state error is what we are interested in. There's a small error between the reference signal R of S and the output for reference signals at frequencies where the transfer function G of j omega is large. That's one conclusion we can make about the closed loop behavior by simply examining or looking at the open loop transfer function, where the open loop could include the plant and the controller itself. Another point that we can take from the open loop is, if I now ask you, looking at the closed loop, typically first thing I'm wanting to know, what's the stability of the closed loop system? What impacts stability in this transfer function? Which piece of all the pieces that are there influences closed loop stability? 1 plus G of S. Now the frequency response is looking at G along the imaginary axis. That's looking at G of j omega. But we are going to be able to infer something about stability, or the closeness of stability. So the stability of the closed loop is governed, as we've learned this semester, by the denominator, which is 1 plus G of S. If 1 plus G of j omega is close to 0, then we know we have a pole near there, since 1 plus G of S is finding the values of S where that vanishes. Now we're looking along the imaginary axis, and if we're marching up the imaginary axis and we find that G of j omega, or 1 plus G of j omega, is close to 0, then we know we are near stability, or instability. So I need to put the I in. We're near instability if 1 plus G of j omega is close to 0. Because at the stability boundary, that's occurring when this would be equal to 0. Or, doing what we've learned how to do, we could relate that to just the transfer function G, by isolating g of j omega in that equation, and we see that that now says, oh, if g of j omega is close to a magnitude of 1 at an angle of minus 180, then we are close to this stability boundary. And for that reason, therefore, we are interested in the behavior of g of j omega near a magnitude of 1 and a phase of minus 180 degrees. And that's actually these 2 points. We're now looking at where in frequency is our magnitude of g close to 1, and where in frequency is our phase of g of j omega close to minus 180. That now gives us an indication of how close to being stable we are, or those are now called our stability margins. Which, if we now sketch those, let me see if I can sketch these. Let's say that's the magnitude, and now let me draw the phase curve. So there is, I shouldn't, and let me do this. So there's the phase curve. Now let me introduce 0 dB. This is now the g of j omega in dB. And now let me introduce another line, but this line now is 180 degrees. And those are actually our 2 key lines. 0 dB is a magnitude of 1, and minus 180. These are the 2 values of our magnitude and phase that we're interested in. Here is the phase of g of j omega. Now, if I ask you to find the frequency where the magnitude is equal to 1, that's not going to be very difficult, is it? Since we know that 0 dB corresponds to 1, we can now simply say, oh, there's the frequency where the gain curve goes through 0 dB, and we're going to label that omega sub g, and that's going to be called the gain crossover frequency. Omega sub g is the gain crossover frequency. We also have a frequency where the phase curve goes through minus 180. We'll call that omega sub p, and that's going to be our phase crossover frequency. Once we've identified those frequencies on the magnitude plot, gives us the gain crossover frequency, and we want to then read down and see what is the phase at that particular frequency, and then the phase crossover frequency we want to read up and see what's the magnitude at that particular frequency, and those will actually provide us with our stability margins, meaning we know we are going to be right on the stability boundary when we're at a magnitude of 1 and a phase of minus 180. Meaning, this red curly brace that I've now included in my phase curve tells us how much additional phase we can tolerate losing at that frequency before we get the magic combination of 1 and minus 180. That now is going to be our phase margin. That's the margin of phase that we could actually tolerate our system losing before we actually became unstable. So this we will call our PM, or phase margin. Likewise, if we go over to the frequency where our phase is equal to minus 180, then how much gain can we allow to be added or increased into our system before our gain moves up to 1, and then we have this magic combination of 1 at minus 180. So this is now our GM, or gain margin. And those are pretty easy to find once you have your frequency response data available to you. Meaning you want your phase, when you have a gain of 1, you want your phase curve to be more positive than minus 180 to give you a stable system. If your magnitude plot was actually larger than 1, when your phase curve crossed through minus 180, you would have an unstable system. You want these margins as defined here to be positive, and these are the positive values that we will be using. If we wanted to improve our phase margin, then we might be interested in trying to make our phase curve do something like that. If we wanted to enhance our gain margin, what we will maybe do is actually make this start breaking sooner, and now we have more phase margin. So there are ways that we can adjust these curves with either the yellow highlight or the blue highlight, or a combination of the two, to enhance or increase these margins, phase margin or gain margin. And that's the whole point of designing controllers or compensators. Compensators or controllers are used to improve or adjust the nominal Bode plot of G of S to improve the gain margin and or the phase margin. Let's now look at a particular system, just so that we're all back to on the same page relative to creating Bode plots. Suppose somebody gives you a G of S that's now 4s plus 5 over s plus 0.1 s plus 20. For that particular system, can you tell me anything about the poles and the zeros, the way that I factored this transfer function? And that one shouldn't be difficult even on an early Monday morning, that question. You should be able to immediately tell me where the poles and the zeros are located. They're in the left half plane. Where's your 0? At s equal minus 5. Do you see the root locus diagram? Do you at least see the poles and zeros? you have a pole near the origin at minus 0.1 and another pole at minus 20 and a 0 in between those two. That has a pretty benign root locus, doesn't it? But this particular structure is what I will call, or what is called, the PoleZero form. And that's not really the form that we want to be using to sketch our Bode plots. But this now, somebody already said that all the poles and the zeros are in the left half plane, and that's actually referred to, or there's a terminology that's used to describe that, and that is that we have a minimum phase system. Which is that all poles and zeros are in the left half plane. Let's just quickly go over where that phrase or that description comes from. Suppose now that I provide two different zeros. I have one at, let's say, minus 1, and another one, I'll say in red, as plus 1. The frequency response is obtained by simply walking up. This is now the S-plane. The frequency response is generated by simply walking up the imaginary axis, or the j omega axis, meaning if I went to that frequency, if I wanted to know the contribution of the 0 in the left half plane, I would know that the length from that 0 to that frequency is given by, let's say, L sub z left. And what's the magnitude contribution due to the pole in the, or the 0 on the right? It's the same concept, and in fact, if it's the same distance into the right half plane as the 0 is into the left, they have the same length, don't they? But what about their zeros? I'm sorry, their angles, or their phase. The phase from that one is that small angle. The phase due to this one is that one. Which of those angles is the minimum? The one in the left half plane. And you can then say, oh, I could look at this frequency and I could look at this frequency. No matter what frequency I look at, the lengths, the magnitude contribution from the left-hand 0 or the right-hand 0 are the same. So you couldn't differentiate these zeros as being in the left half plane or the right half plane based on their magnitude behavior. It's going to look the same. It's when you look at the phase that they are going to be different. Now, the 0 in the left has a smaller phase relative to the 0 in the right, and that's where this minimum phase 0 terminology comes from. So this is the minimum phase zero, the one in the left half plane. The reason is because we have these two different we're looking at two different factors. Those aren't both in the same system. I now have a blue system and a red system. I have a blue team and a red team. We have two different zero factors, which, summarizing what we just talked about, let's say we now have the left zero factor. That's this s plus 1. Which now, if we set that equal to 0, we have a 0 at minus 1. And we can contrast that with our rightmost factor, which now looks like s minus 1, and that's now over there at plus 1. Which, if we wanted to find, if I labeled these as, let's say, L sub ZL for the length of the 0 in the left half plane, or this is L sub Z right, the distances is now this length, and over here just by using or replacing S with j omega, now we're comparing the magnitude of j omega plus 1 with the magnitude of j omega minus 1. And if you found the magnitudes, it's just the real part, which is 1 or minus 1 squared plus omega squared square rooted. Those hypotenuses are the same, which we've already shown by comparing. Then if we wanted to look at the phase, that's now the angle associated with j omega plus 1, and over here, this is now the angle of j omega minus 1. And the angle is where this minimum phase, so this is now the theta sub right. Is that what I called it? No, Z right. And this is theta Z sub left. And hopefully it's clear that the one on the left is the minimum phase, and the one on the right is actually called non-minimum phase. Here's the minimum phase. And this is the non-minimum phase 0, which we are going to concentrate on the minimum phase, always having our poles and zeros in the left half plane. But if somebody says, oh, you have a non-minimum phase system, where are you going to have a non-minimum phase system? Your bicycle. It has a right half plane 0, which makes it more challenging to control. Right half plane zeros are problematic. As we've learned, if we have a 0 there and we had a pole at the origin, you have an unstable system with a positive gain, don't you, in the root locus. So the non-minimum phase zeros do introduce more challenges, but to learn, for now, let's just focus on having minimum phase transfer functions. If nothing is stated, you can just assume that we're dealing with a minimum phase system. Is that clear? Now we know from the system above that we do have a minimum phase system because it was easy to see where our poles and zeros were in that PoleZero form. But to sketch the Bode plot, we want all of these constants in those factors to be normalized to 1. And then that doesn't change with frequency. Those will be fixed. And now what we want to do is we want to convert that transfer function into time constant form. If we factor out a 5 from the numerator, we've now normalized that constant to 1. Downstairs, we can factor out the 1/10 from the first factor, and we can factor out the 20 from the second factor. And if we clean that up a little bit by simply combining all of our constants, 4 times 5 is 20, and that cancels conveniently the 20 downstairs, and we just have 1 over a 10th, or we now have 10, s over 5 plus 1 over s over 0.1 plus 1, s over 20 plus 1, and that's now our time constant form that we want. From this particular system, before I even start sketching a Bode plot, a lot of times I like to see what are some key ingredients or what are some key properties or key features for the particular system that I'm trying to sketch its Bode plot for. One thing that you can see from this is I do not have any poles or zeros at the origin, do I? I don't have any S in isolation. For this particular system, I have no poles or zeros at the origin. I just have linear factors. What's another key piece? One piece that we like to focus on when we were sketching root locus was the difference between the number of poles we had and the number of zeros, our PoleZero excess. And that's important here also. What's our PoleZero excess for this system? I didn't hear anyone bidding higher than 1, and 1 is correct. We have 2 poles and 1 zero. What does that tell us about the Bode plot behavior as we get higher in frequency? What's G of dB going to be doing? The magnitude, it's going to be sloping, isn't it? As if you just had a single pole system, and if you have 1 pole, what's the slope? That's this minus 20 dB per decade. Meaning when we get to high frequencies, we should see our magnitude rolling off at 20 dB per decade. In being consistent with that PoleZero excess of 1. What do we know about the phase of G at high frequencies if we have a PoleZero excess of 1? Where's that going to be approaching? What angle? And now what you could do is you could say, well, if I have effectively a single pole, what's the phase contribution of a single pole? It's going to be 90 degrees downstairs, so it's a minus 90 degrees. We should be seeing our phase then approaching minus 90 degrees as our frequency gets higher. For this particular system, where does our magnitude begin? And this is one of the nice things about putting this into time constant form. All of those factors now are not contributing any magnitude at low frequencies. At low frequencies, all of those S's we're replacing with j omega, but we're making omega really, really small. That gets dominated by the 1 in each of those factors. And the log of 1 is 0. All of those factors, other than the constant sitting out front, don't contribute anything at low frequencies relative to the magnitude, which is why we factored it into this time constant form. What's the magnitude of that at small frequencies? It's 10 in absolute terms. In terms of dB, now we just have to remember log 10 base 10. That's 1. So we now have 20 times 1. Our magnitude plot is actually going to begin, and it's going to be flat at 20 dB at low frequencies. Then we can start thinking about breaks in our magnitude plot, and I like to sort of go from low frequencies and transition. The lowest frequency that we had was a pole, and that was at 0.1, and what's going to happen to the magnitude at 0.1? We're flat until that point. Then what happens? up or down in terms of break? Down, because it's downstairs and it's a pole. Then we run into a 0 at 5, and what change in the magnitude break-wise is going to occur there? Up or down? Up, because it's upstairs. And then we have a pole at omega equal to 20, and that's going to then cause us to break down. Now with that, armed with that information, we can quickly sketch these curves. Let me go ahead and, here's the magnitude. I'm going to be flat. Well, maybe I should put my axis here, but well, until I reach 0.01. And then I'm going to start going down, aren't I? Until I reach what frequency? And that's where these up and down arrows are convenient. Now I need to go over to omega equal to 5, and what you might do, just to make it easier, is you might actually do some plot on your paper. You could say, oh, what happens at 2? That's roughly 0.3, so that's 30% of the distance between the two decades on your axis. At 3, it's 0.48, so that's roughly 0.5. At 4, it's 0.6, and let's say at 8, it's 0.9. And if we wanted to do 5, it's at 0.7, roughly. Those give us the relative spacing, so that now we have a 0 occurring at 5, which is between 1 and 10, but on this log scale, which I usually just label it as omega, we're now 70% of the distance between 1 and 10, because log of 5 is 0.7, roughly. So now we can go over here to 0.7, and at that particular point, now what do I know about, I started here at 20 dB. And let's say this is 0 dB. This is now G of dB. I now know that after a decade, I better be down 20 dB, shouldn't I? So my gain curve is going to be sloping with that slope until I reach 5. And at 5, I now go up in terms, or I change my slope by plus 20. Now I'm going to be flat until I reach 20, and 20 is 30% of the distance between 10 and 100. So now I say there's 20. And now what happens at 20? Now I go down again in slope, and there's my magnitude curve. Is that okay? Then I can do my phase curve. Hopefully I could be somewhat aligned. And now what do I want to do? Well, I have a break at 0.1, and my phase is equally split across 2 decades. And where am I starting? I'm starting at 0 degrees. But at 0.01, I start going down to minus 90. And then at 5, I am right here, but I need to kick in at 0.5, and I need to kick off at 5. So that particular 0 gives me something like that. And finally, I have something at 20, which is 30% of the distance there, but it kicks in at 2 and off at 200. And it now, wherever I started, is right here, out to here. And if I add all of those together, I now am going, and then I go down, and then I am flat. Whoops. Here's where you have to wake up and remember that your slope changes when curves start to kick off. And now what am I doing? Now I'm going flat again until that happens at 5, and then I come down, and there's now my phase curve. Whoa, I'm way out of time, aren't I? So now think if that is stable or not, but that should be your phase curve, and we'll pick up with gain margin and phase margin and controller design next time.